too, because I mean my disk is not full. I mean, some of the disk contains useful data. Some of the disk is not used. So why do I take the backup of all that stuff? So I should not. Okay, so pure physical dump systems, they don't work very well. So you don't, no value in backing up the unused disk blocks. But if you don't take the backups of some of the blocks, then that means that you need to remember the block numbers. In that case, you need to write the block numbers into the backups too. So that would be an extra field if you are not taking backups of some of the places. The other thing is that bad blocks are always present. Okay, I mean the disks are not perfect; they fail. Even from the factory, some of the blocks are bad. So so what do we do with the bad blocks? You should not take backups of those bad blocks. I mean, since this is a physical dump, it doesn't know if that bad block is a file or not. So usually the operating system creates a dummy file that contains those bad blocks. That dummy file is never opened by the operating system because it is hidden. That dummy file contains the inode addresses of those, the block addresses of those bad blocks, and physical dump systems do not dump the blocks of those kind of files. Okay, they are fast, but they are unable to skip selected directories because physical dump systems, they don't know the file structure. Okay, all they know is the blocks. They don't know the file structure of the directories, or they cannot do the incremental dumps because they are not reading the. How do you do the incremental backing up? What do you need for the incremental backup? What kind of information do you need to do incremental backup?
Last modified.
What's that?
Last modified.
Last modification time. Last modification time of the files, but we don't have last modification time of the blocks, right? The last modification time or last access time is for the files, not for the blocks. So the incremental dumps is not possible for physical dump. Okay. And what else? And from the physical dumps, I cannot restore individual files. Most of the time, when you are restoring your file system, you don't restore the whole file system. You restore one or two files, okay, that you need. So for the physical dumps, you cannot achieve restoring individual files. So what is the alternative for the physical dumps? The alternative is the logical dump. What do I mean by logical dump? It doesn't start from the block number 0 and back up all the blocks starting in order. Instead, it asks you for a directory and it backs up all the elements of that directory and subdirectories, including the files contained within those directories. Okay, starts at one or more specified directories and recursively dumps all files and directories found there that have changed since that have changed. That means that logical dump systems can do incremental backups. Okay, so you give the directory names and you give the last backup time, and it backs up all the data under those directories. Okay, so there is a very compact and popular backing up algorithm that comes from Unix days, and we are going to look at that algorithm. This algorithm, it dumps all directories, logical dump. Okay, it dumps all directories that lie on the path to a modified file or directory for two reasons. Okay, let me give you this example, and I will return to this part of the slide. Let's say this is my root directory. Okay, these are my subdirectories, and within my subdirectory there are subdirectories, and these shaded elements, they have been modified since the last backup time. Okay, The shaded items have been modified since last dump. Okay, so my task is to back up this system. How do I do this? So there is a 4-phase, 1, 2, 3, 4-phase algorithm for doing this. Okay, for doing this. In the first phase, for each modified file, its inode is marked in the bitmap, and each directory is also marked whether or not it has been modified. So I keep a bitmap representation of this file system, and for each modified file, its inode is marked in the bitmap. I have a bitmap of inodes, and for each directory I do the same thing too. So this is my this part A is my bitmap, and I mark all the files modified, also all the directories that contains those files. So let's check which ones are modified. Let's see. So do you think 4 will be marked? No, because 4 is not changed. How about 2? 3 is going to be marked, right? Because 3 has changed. How about 2? Is 2 going to be marked as changed? The answer is, well, it seems no, but the answer is yes. 1, 2, 3. Only 4 is not marked. 1, 2, 3. Only 4 is not marked. Why? Why did we mark this 2?
3 değiştiği için mi içindeki?
Yes, for the directories there is a special reason. For the directories, you either mark the directory because it is modified, or you mark the directory because it contains some files or directories that are modified. Okay, so 2 is marked because 3 is modified. Okay, 7 is marked because 8 and 9 are modified. Okay, how about 10? Is 10 going to be marked or not? 10, no. Yeah, right. These 10, 11, 12, from 10 to 15, they are not going to be marked. So from 10 to 15, 10 is marked. Well, at the end, okay. The rule for the first phase is this. Okay, sorry. For each modified file, its inode is marked in the bitmap. For each directory, each directory is also marked. So for the first phase, so I made a mistake, sorry. For the first phase, you marked all the directories, whether it is modified or not, but you only mark the modified files. Okay. So that's the first step. So these are this one, 4. And okay, I have 6, 4, 7. Only 7 files that are not, or 8. Only 8 files that are not modified. So let's look at them. 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6, 8. Only 8 files. How about this? This is not 9. Okay, 8 or 9 files, I don't know. There are 8 or 9 files that are not modified, so they are not marked. The rest of them are marked. So the phase 2, this should be phase 2 walks the tree again, unmarking any directories that have no modified files or directories in them. So this is a 2-step algorithm. Now we go back to our tree, and we unmark any directories that have not been modified, that have no modified files or directories in them. So what we do is, see, this is what happens. This is the same directories and the files. Right? These are either the files or the directory that contains those files. So 10 to 15. From 10 to 15, also, yeah, this part, right? This part should not be marked as marked. From 27 to 32. Yeah, 27 to 32. So the second step is this one. Let's look at the third step. Scan the inodes in the numerical order and dump all the directories that are marked for dumping. Okay. So for the phase 3, dump all the directories that are marked for dumping. So I dump this one, 4, 5, 6, 7, 5, 6, 7, 16, 18, and it goes like that. So this step dumps all the directories. Once I dump all the directories, I dump all the files. Okay. So this is the algorithm for a logical dump, classical algorithm. It marks only the modified files and directories, and dumps the directories first and then the files. Okay, incrementally. So we need to dump this directory too, even though it is not modified, or this one, even though it is not modified. Otherwise, I cannot keep these files in a consistent place in the dump. I need to dump this directory too, even though it is not modified, because without this one, I would not know the relationship between these files. Restoring the backups would be very, very difficult, even if I don't backup unmodified directories. Okay. So why do I need this? I need to have such a backup mechanism to transport the entire file system between computers. I mean, if you don't backup those file directories, then you will have problems. Also, I need that to make it possible to incrementally restore a single file. Restoring becomes a problem if I don't backup those unmodified directories. Okay, any questions about backing up? Okay, if there are no questions, then I will continue. File system consistency is a very serious issue for all types of operating systems. File system consistency means that when you are doing important stuff with your disk data, for example, you loaded a file, okay, you modified it, while you are writing the file back to the disk, something happened and your system crashed, so you have very inconsistent file on your disk. So some of your files might be inconsistent because your system has crashed while you are writing to the disk. Since the files are very, very large, it might happen, right? Sometimes it takes a whole minute to write a PowerPoint presentation to the disk. When your computer crashes while you are writing it to the disk, there is going to be a very serious problem with your file. This is a very serious issue, but there are even more serious issues, like when you are writing your I block, when you are writing a block that contains your inodes only. I mean, that's a system file, a block that contains the inodes. When the system crashes, when you are writing such a block, your system becomes unstable. And you are not losing a single file, or you are not losing 2 or 3 files. You might lose your whole disk file system. That's a very, very serious issue. So operating system has developed many techniques to address these kind of problems under this topic, file system consistency. That's the main reason why we are looking. These are the main reason why we are looking at these problems. Either you lose your data, or critical problems if some are inode blocks. If you are writing inode blocks or directory blocks and your system crashes, there could be some serious problems. So for this, both Unix and Windows has utilities to check the file system consistency. For Unix, it says FSCK, file system check. For Windows, again, it is file system check. These are the Windows and Unix utilities. And usually when your Windows system crashes, okay, if you don't shut down your system, if you directly turn your system off, okay, when you start your Windows system, it asks you a question. What is that question? It says that, should I start Windows normally, or should I do some file checking or something, right? So it is trying, it thinks that since system has crashed, it shut down inappropriately. There could be some problems with the disk. So let's check if the file system is consistent. That's what we call file system consistency and how to check it. Okay. File system consistency. We are going to look at this simple algorithm for block consistency. If my blocks are consistent, there is another algorithm for file consistency, which is similar. Consistency. So I'm going to look at this block consistency. When these utilities start FSCK or FSC, they run a process similar to this. These utilities keep two tables. Okay, one for keeping a counter for each block. The other one is keeping the counter for the empty blocks. Okay, so let me show you a table. Okay, these are, let's say I have a very small system. I have only 15 blocks. Okay, I will have much more than that, but let's say I have 15 blocks. So I am keeping two tables, one for blocks in use and one for free blocks. Okay. These are not the binary, by the way. These are integers. So this is the algorithm, how it works. The counters in the first table keep track of how many times each block is present in the file. And usually this should be either 0 or 1, okay? Usually this should be, for a consistent file system, these numbers either should be 0 or 1. Because this block could be a part of a single block, could only be a part of a single file. Either it's a part of a single file or not. So it should be either 0 or 1. And we do the same thing for the free blocks, okay? If a block is free, it should be marked as 1, otherwise it is 0. A block cannot be 2 times free, okay? So this should not happen, okay? The counter in the second table record how often each block is present in the free list. Remember, how did we keep the free blocks in the disk? We had either a bitmap version or a linked list version. Before starting, yes. See, these are the free blocks. Let's say block number 42 is free. Let's say somewhere in the list I have 42 again. That means that 42 is listed 2 times as free. That shows me this is a problem with there is a problem with the file system. It's an inconsistency. So it could happen with the linked list version of the free block list. I cannot have the same problem with the bitmaps because bitmaps shows you either it's 1 or 0. So this problem will not happen with the bitmaps. So I have two tables, one for the blocks contained in a file and one for the blocks listed in the free list. And what we do is we read all inodes and we mark the tables. What are the inodes? Inodes are the data structure that contain the addresses of the blocks for each file. So I read all of those inodes. For each block referenced by a file, I mark its number, I increment that number by 1, and I completely fill my first table, and I do the second table. I examine also the free list or bitmap to find all the blocks that are not in use. And I have pictures like this at the end. For this one, for this case A, part A, I cannot erase this, sorry. Maybe, no, it doesn't work. For this one, ignore this 2 here. For this one, everything is okay. A block is either occupied or empty, So I don't see any inconsistency. So when I run my checklist utility, I don't see any problems. Let's look at this one. Do you see any problems here? Any problems? What is the problem? Which block has the problem?
2.
This one has a problem. It says that this block is not used by any file because it is not referenced, but it is not in the free block list either. So what causes this kind of a problem? What do you think happened that caused this problem? There might be several reasons why we.
Orayı kullanamayacağız.
This is a problem. The question is, what created this problem? That would be the second question. Yes.
Disk dosya diskten silinmiş olabilir ama o silinme işlemi yapılırken crash olmuş olabilir.
Yes.
Ya da yeni bir dosya oluşturulurken crash olmuş olabilir.
Yes. Those are very good examples. I am removing a file, typed rm file name. Immediately it removed the file from the directory list. The system crashed and the system couldn't find time to mark its block as free. So this might happen. Okay. So somebody removed, or somebody created a file, but while creating the file, it created a directory entry, but it couldn't find time to create any blocks. That might be another reason. So this is not a very serious problem actually, because it doesn't hurt, because nobody is referring to it. Okay, but since nobody is referring to it, I am losing that space. So it's a waste of this space. That's the problem. So how do you solve this problem? Once you realize it, how do you solve this problem?
O blok tamam.
Yüksek sesle söylesem ben